would like to do now is to have a presentation that will help you in your development of your assembly code. In particular, what I'm aiming this at is the debug of the assembly code. Right now there's a file that the Trambler creates, sim.sim, that we haven't been using, but it's created in order to allow us to do what I'm about to show you. 460 is a class that teaches the concepts of system-on-chip design. Whenever you talk about system-on-chip, what's implied is that there are two aspects to the issue. There's the hardware aspect and the software aspect. We'll spend a lot of time on our hardware design of our SoC device, but what we're talking about now is the software design. How do we have an efficient development cycle? The software in our course is based on the Xilinx 8-bit PicoBlaze, but now we have an emulator called the TramelBlaze that's a 16-bit version. All of the documentation that I've given you shows you all the instruction set, how to program it. I'm going to keep producing information to help you there. So we should be able to create our code now, but the problem comes in when you run it, it doesn't do exactly what you want it to do and you want to change it. But right now, when we change it, we are going out and going back to the Xilinx tool to have it create another ROM. And that process ends up taking quite a bit of time. So we want to come up with a scheme that allows us to take our newly assembled code and run it immediately without having to create the ROM. The approach requires the use of a Verilog memory. We'll see in the new TramelBlaze top sim, there is the system function $readmem, which will take an ASCII text file in a hexadecimal format and load the contents of that file into a memory that you've defined in your Verilog program. So right now the TramelBlaze top.v instantiates the TramelBlaze engine along with the TB-ROM module that we create using the tools. What I'm offering here is a second version of the TramelBlaze top called TramelBlaze top sim. What that means is that you're going to have to go into your Vivado tool, to go into your project. You're going to remove the TramelBlaze top from the project. Don't delete it, just remove it. Then you want to add TramelBlaze top sim. That will then allow you to take advantage of this rapid development cycle. When we look at the files, on the left we see what we've been using so far. It's the TramelBlaze top, where we see the engine instantiated, and what we see below it is the instantiation of the memory that we create using the Xilinx tools. That is still the approach that you're going to need to take when you want to program the FPGA. But typically, you don't want to program the FPGA until you've convinced yourself that what you've created works. And we prove that it works to ourselves by simulating it and then observing the results on the simulator and confirming that it does exactly what we want. So on the right, you see it's the same instance name. It's just the file that's different. We instantiate the TramelBlaze top and then the TramelBlaze engine. And then below it, now you can see how we've defined the Verilog memory and then how we've utilized the system function to copy the sim.sim file in. Notice that it's a relative path. So it took me quite a while to snoop around the construction of the directory structure under Vivado to get the right path. This path assumes that you've created the assembler directory at the same level as your project directory. If you have your assembler and your project directory at the same level, this path will work. And when you run your sim, and we'll see an example of this a little bit later, you'll see the contents of the memory available to the simulator. So again, we're using this approach on the right when we're debugging the design of our assembly code for the FPGA. So the TramelBlaze top sim must reference the sim.sim file. Mentioned there's the relative path. So for this to work, again, the assembler directory must be found at the same level as the project directory. So in this directory is where you find the trambler, you find your TBA file, you find your .coe file, you find your sim.sim file. This directory is where you will find the Vivado project file. It will be inside this directory. With that, the relative path as given works. So when developing your software, you need to ensure that the design source for the TramelBlaze top is the TramelBlaze top sim. You can see that here. There it gives you the instance name. There it shows you the file that that instance came out of. When you make the swap, you may see still the TB-ROM in the list of modules that are available, but it's currently not instantiated in the design. That's okay. You don't have to delete it. You can leave it. For when you come back, you can then recreate it. By going back to the TramelBlaze top, it will immediately bring the TB-ROM back into play. When you run your simulation, you should be able to add the instruction memory to the waveform. In this case, you'll see the memory 4K by 16, and it looks like this when you add it. And across the path, you can see all the entries in the memory, but it gets unwieldy pretty quickly. But if you expand it, you can then see, oh, location 0 has this, location 1 has that, location 2 has that. So a quick little check can help you confirm that you have properly loaded your sim.sim into the memory. When you run your simulation, you should add the instruction bus and the address bus to the waveform. And that allows you then, as you're running your simulation, you can see the sequence of addresses that the TramelBlaze is fetching and executing the instructions from. Along with that, in the upper row in the instructions, you see what is the contents of each of these address locations. Now, how do we use that when we do our debug? We need to use it in cooperation with the list file. The list file I've attempted to create such that I output the address and then give the instruction along with the text from the initial assembly code. So load point with zeros is at address 0, and it's implemented with an AE00 0000. Then load value with 1, 2, 3, 4 is here, address 2 and address 3. The shortcoming in my tool right now is I don't have the address here, but this is the content. So 76. So this should be 0, 1, 2, 3, 4, 7603, 0, 1, 2, 3, 4, 7603. So you can still trace and see what's going on. So the goal is, by observing how your assembly code is sequencing through the code, you can follow along and see what's happening. When you do have problems, you can add other parts of your design to the simulation and say, okay, at that point in time, what did I write? Or at that point in time, what was the contents of this? So when you realize something's wrong by looking at the way the simulation ran, you want to make a change. So we edit our TBA file and we run the trambler again. Today, what you need to do is you need to then launch the Xilinx tool to create the memory, and it takes too long. Here, we're going to take advantage of the fact the trambler creates an updated sim.sim file immediately. So the methodology or the approach is don't close the simulation. Leave the Xilinx tool running. You jump into your directory where you have the trambler. You make the edits to your TBA file. You reassemble it by launching the trambler. Then come back to the Xilinx tool and just restart the simulation. This button here will restart the simulation. That means it takes the simulation back to time 0. Then when you tell your simulation to continue, either by telling it to run a certain period of time or just to run until you pause it, it will then load the sim.sim file, the newly created sim.sim file, into the memory, and off you go. It is a much faster way to debug your code than the approach where you have to create the memory. So the purpose of this approach is to allow the rapid development of the assembly code for the TramelBlaze. To use it effectively, you need to spend time to get the routine down. Familiarity is essential. If you just do it once and come back to it 2 weeks later, you're not going to really have a clear understanding of what it is you're doing. Take the time to play with it. Take the time to understand what's going on. And what it will do, it will translate into productivity. You'll be able to crank out your TramelBlaze assembly code very quickly. So the ability, what I've given you here, is to have an immediate feedback when you change your code. This will be a huge time savior. So what I'd like to do now is I'm going to stop this discussion. Then I'm going to come back with a discussion showing how you use the tools. Just a simple demonstration of how it works. So the first thing I want to do is show you what I'm looking at here is the directory. The assembler directory is at the same level as the processor directory, the project directory. So in the project directory is where the Vivado project file is. Then in my assembler directory is where the trambler is and where the sorted source code is. So what I want to do now is make a change. So in my code right now, I have the load of my initial pointer to zeros. So imagining I had done something I didn't want to do, I'd say, okay, I want to change this. So now instead of zeros, I want to load 3, 4, 5, 6. So then I can save the file, come back in, launch the trambler, tell it my file is sortit.tba, run it. What happens now is that a few files get created. So let's take a little peek. So let's first look at the list file. Now, once we get to the executable code, we can say, okay, now instead of loading point with zeros, I'm loading it with 3, 4, 5, 6. The line I've commented out is there. We can then say, okay, let's look at the sorted.coe file. And this is the file that's in the format for the Xilinx tool to create our memory. He has his own format, still an ASCII file. Now let's take a peek at sim.sim. Sim.sim just has all of the hexadecimal values. It has one entry for every location in the memory, so there's going to be 4096. And I can see, okay, there's my 3, 4, 5, 6. So now what I do, I hadn't launched a simulation, so let's come back, let's launch sim. I'll show you how it works when I put it back, how quick it is. So let's go ahead and launch our simulation. And if it doesn't take too long, we'll soon see our waveform display. And let's just take a peek here. You can see there's the instruction memory bus, the instruction bus, showing the addresses of each instruction. There's the contents of the instruction. There's my 3, 4, 5, 6. If while I'm running my simulation, I want to see the contents of my register, I can add the register file from the TramelBlaze. There I can see the contents of all the registers at that point in time. And then here is the memory inside the TramelBlaze top. And you can see the load register A followed by the 3, 4, 5, 6. So this gives you insight into what's going on. Now, what we realized is, oh, that isn't the change we wanted to make. So what we do is we come back, we say, let's go back, change our TBA file. So come back to where we were. Get rid of the bad instruction. I now save my file. I come back to my directory, launch the Trambler, sorted.tba. If I'm at all concerned, I can come in and look at my list file, let's say, sorted.list. Now we get down the executable code. Oh, now I see I'm back to loading with zeros. If you recall, last time was the 1, 2, 3, 4, or the 3, 4, 5, 6. So now all I want to do is restart the simulation. When I restart it, now I can either just tell it to run forever or run for a given period of time. That's what I'm going to do now. When I click the run, now I come back to observe the results. Now we can see the change has taken effect. There's the load register 0. Now I'm back to loading it with my zeros. So it really is a very quick way to turn around changes to your assembly code and then to observe the impact in the simulation. So I hope this helps. Hope you guys are able to become familiar and use this and have confidence in the tools so you can get through these projects in a timely manner.